Hello. Today we're going to talk about curl and divergence. So this is going to feel very different from what we've been doing. We just finished up with line integrals and we're about to get started on surface area and then surface integrals. But in between, we need to learn a couple more operations that we're going to be using in order to handle this concept of using integrals to calculate surface area and then using integrals to integrate over a surface area. So in this section, we're going to learn two more operations with the del operator. And just to remind you, the del operator is this upside down triangle del, and it is a vector with components that are operators. They're not actual functions, they are operators. They operate upon functions. So you've got del del x, del del y, and del del z. Now, if that vector was to operate on, say, a scalar function, little f, then what we would get is a vector with functions in it. And each of the functions would correspond with a first partial derivative of that little scalar function f. So that's what we did before. We had del f, and that calculated the gradient vector. And now we're going to look at what happens if we do a cross product with a del operator or a dot product with a del operator. And we're going to start with the cross product for curl. So the curl of a vector field is what we get when we perform a cross product with the del operator and then a vector field. So I have this set up here. Our notation when we're calculating curl of f is just curl of f. And it's of f, big F, the vector field. And so you might see this notation right here where it's just that upside down triangle crossed with f. And what you need to know and remember is that you're going to be taking two vectors. One of them is the one with the first partial operators, del del x, del del y, and del del z. And then the other one is the components of f. So we set those up in a cross product calculation using determinants, where the first row is your ijk, second row is going to be your operators, and the third row is the pqr components of f. And after you do the calculation of your determinant, what you come up with is this vector right here. And this vector is just the result of having calculated the determinant. I'll do an example in very soon so we can review calculating a determinant, but we have been doing this throughout the semester, so this is definitely not brand new. But the result that we get is something that you can either memorize or you can calculate each time. I usually just calculate it each time because I don't want to get it wrong just because I accidentally memorized it wrong, okay? But for this first question that I'm going to ask, I am going to use my memorized form, okay? So in this question, we're being asked if the r component of f is equal to 0, and p and q are only functions of x and y, then what is curl of f? Okay, so here is what f is based on what they're saying. They're saying that p and q are only functions of x and y, so let's write p of xy and q of xy and then 0. Okay, that way I'm going to use my my memorized form that I don't have memorized to see what happens. So if I have curl of f, that's supposed to give me the vector with components del r, del y, minus del q, del z. The second component, if I distribute the negative sign, it is del p, del z, minus del r, del x. And the third component is del q, del x, minus del p, del y. And we want to know, what does this become? Hold on, that should not be a bracket, that should be an angle bracket. Okay, so if I try to find del r, del y, I'm going to go up to my r component in f, and it's 0. So the derivative of 0 with respect to any variable is just going to be 0. All right, then if I take del q, del z, so I'm going to go to my q function. Q is just a function of x and y. So if I take the derivative with respect to z, the whole thing will go to 0. Okay, so my first component's 0. Del p del z, I go to p and I remember, oh, it's just a function of x and y, so del p del z is 0. Del r del x, r is 0, so all derivatives of it are 0. Okay, not getting much here. Del q del x, if I go to q, q is a function of x and y, so I'll just get del q del x. It'll be non-zero. Okay. And del p del y, well, p is a function of x and y, so del p del y will be some non-zero value. And this is the result of the curl of my vector function that has a 0 in the r component and only functions of x and y in the p and q components. Look at this here. Del q del x minus del p del y. That should look familiar. This is the integrand from Green's theorem. And then also notice that if del q del x is equal to del p del y, we have to remember, like thinking back on what we've done already in the line integral, when we were looking at the fundamental theorem of line integrals, if we had the del q del x was equal to del p del y, then that means f is conservative. And it also means then that the curl of f would be the 0 vector. So that's an interesting concept to pull out just from one calculation that we've got here. And it may not be totally obvious, but I just want to point out, like, this is something that we've actually seen before. We saw it in two different things, del q del x and del p del y. First was showing that they're equal would allow us to say we had a conservative vector field. Second, when we used it in Green's theorem in order to relate a line integral to a volume integral. And then it turns out that if we do have a conservative vector field, then that whole curl would end up being 0. We'll go back to that in a moment. For now, if f of x, y, z has components x, z, x, y, z, and y minus y squared, find the curl of f. So we're just going to go ahead and calculate. Here's how I set it up. Curl of f is equal to, and then I have to remember this, it's going to be that upside down triangle vector crossed with f. When I write it this way, this reminds me what the pieces are. Just writing curl of f, that's a whole new vocabulary thing, right? We got to get comfortable with it. We got to know what it means. What are the operations that happen with it? So it's going to be del cross f. So I set up my determinant. First row is the I, j, k. Second row is going to be the operators, del del x, del del y, and del del z. Third row is going to be the components, x, z, x, y, z, and minus y squared. So the first time, for maybe first couple of times I do this, I will show all of my work in all of its gory detail, because that's more helpful than just leaving it, skipping all the steps. So remember, with a cross product, we start in the upper left-hand corner, and we imagine that that row and column are crossed out so we can focus on the 2 by 2 determinant that remains. So when I write this out, this is going to equal I hat times, and then I'd have a 2 by 2 determinant calculation. So this component is going to be del y of minus y squared minus del z of xyz. Okay, that's my I component. Then I can go ahead and erase those, and I move on to the second component, j. I have to remember that there's a minus sign over that. I cross out the row and column that j is in so that I can focus on, my 2 by 2 determinant that I need to calculate now. So with the minus j hat, now I'm looking at del x of minus y squared minus del z of xz. And that takes care of my j component. So let's go ahead and move on to the next one. And the last one, we go to k hat, whoops, cross out the row and column that it's in, and so we can focus again. And so we get plus k hat, and then the 2 by 2 determinant calculation is going to be del x of xyz minus del y of xz. All right, so I never took a single derivative here. All I did was just set up what has to happen, and now I'll go ahead and do all the work. Okay, so the I component, I end up with minus 2y for the derivative of minus y squared with respect to y, and then minus xy for the derivative with respect to z of xyz. I still have my I hat there. Minus, and then del x of minus y squared is going to give me 0, and del z of xz will be minus x, and then I have my j hat. And then plus del x of xyz will be yz, and del y of xz will be minus 0. Excuse me, k hat. Okay, I usually do one final rewrite on these, and I do tend to switch over to the angle bracket notation just because for my eyes it's cleaner and easier to see. So my I hat component, that corresponds with the first component in the angle bracket notation, minus 2y minus xy. Then I have a double negative in the j hat component, so my second component is positive x. My third component is positive yz. And that's my final value for the curl of f. Okay? Pretty straightforward calculation, a little bit tedious, but totally doable. Okay? Now we want to talk a little bit about what the curl vector is. So if our vector field is the velocity of a fluid flow, then there are going to be particles at some point in the fluid. Like we could pick a point in the fluid flow and we could ask ourselves, does the fluid just go past that point or does it start to rotate around it? Okay. If there's any sort of tendency for the fluid to rotate about like an axis that's right on that point, then we would have positive curl. So curl is just measuring rotation. That's it, at a point. Okay. And so a couple of things to point out in here is like if there's no rotation, then the curl of f is 0. They say, or I wrote it here in a different order. I said if the curl is 0, then there's no circulation, right? So we might do a calculation first and make a conclusion, or we could look at a vector field, see that there's no rotation, and conclude that the curl must be 0 or close to 0. If we were to look at the magnitude of the curl, because the curl of f is a vector, so the magnitude would just give us one number, and what it does is it tells us how rapidly it's rotating, okay? When there is no circulation, we say that the vector field is irrotational. Irrotational is such a new and weird word. I like to actually go ahead and clarify it. It means does not rotate. Or I should say does not circulate around the point. Okay, so below I have this little picture, and that's a stagnant picture, right? It's showing a vector field that goes round and round and round. And I can't remember which function I used in order to come up with that vector field. But the vector field is in blue. And then there's a curl vector pointing out of the box that is the curl of the vector field in red. So what I want to do here is pull out something that is something you can see. And I have CalcPlot 3D pulled up, and I have a sample vector field in here. And this vector field is just a 2D vector field. has components 2x and 2y, which came from a scalar function x squared plus y squared. Okay, so simple scalar function. I took the gradient of it and I found 2x and 2y are the components. Now, I've got my components in here, 2x and 2y. My p is 0 because there's no z component. I have my vectors scaled by a factor of 6, just so that they're not like, totally taking over my screen. Along the x-axis, I have 9 points where there was a vector calculated, and along the y-axis, same thing. Along the z-axis, I have 5 here, but really it's just 1 because this is a 2-dimensional vector field. And I've restricted my view to 2D. If I uncheck that box, I see an octant with the vector fields on the xy plane, which is great and all, but I'd really like a better view, so I go ahead and do that. Down here, I have object at 2D clicked point. And right now it's set on this flow line solution curve. I'm going to click on the drop down menu. And look, there's curl at a point. So what this is going to allow me to do is drop a curl vector on any point in my graph. Notice it's not moving. Also notice at the top of the screen, it says curl at point, and it gives the point where I dropped that, and it says it's 0. And it keeps saying that it's 0 everywhere I drop a point. Now remember I said that I got this function by taking the gradient vector of x squared plus y squared. The gradient vector is a conservative vector field, right? And if we're dealing with a conservative vector field, we just learned that the curl would be 0. So this makes sense that we're seeing 0 rotation no matter where we put this curl, okay? Let's change this up a bit. I'm going to go ahead and change my second component, to 2xy squared, and I'm going to see how it changes. It's not very pretty. I think one of the things I want to do here, because of the way my vectors are, is I'm going to use fixed length for all vectors, just so we have a better picture of what's going on here, okay? Then I also want to zoom out a little bit. Oh, maybe that's too much. Maybe I'll zoom back in. Maybe it was just good where it was. We'll leave it like that. Okay, now I want to get this curl at a point. I'm going to drop a curl vector. Look at that, it's spinning around. Up at the top, the curl at the point where I dropped it is 1.9277. It's a little hard to see with my toolbar being viewable there. But so this is a positive curl. It's 1.9277 k hat. Remember, curl is a vector. So what we got was 0 values in the I component, j component, and we got a positive value in the k component. And that's because we are dealing with a 2D vector. This is like that question I asked in the beginning. What happens if r is 0 and p and q are only functions of x, y? Well, that means our curl will only have a non-zero element in the third component. So I'm seeing that I've got some spin here at this point. I'm going to drop it somewhere else. Look how much slower it is. Look how fast it is up there, 5.353. What happens on the, whoa, super fast on the y-axis. What happens if I go down? And if I go really high up on the y-axis, it's spinning like crazy. 11 is the value of my curl. On the x-axis, we have pretty much 0 motion. And what we can see on the x-axis is that there are little vectors on the x-axis that are just pointing straight. So what that's indicating is that the vector field itself just passes by the point, doesn't make it spin at all. There's no rotation at any point on the x-axis here, or close to none. If I go right at the origin, still 0, but if I start to travel up the y-axis, I start to get a little bit of motion. This is just something for you to observe, okay? But this example is a vector field that is not conservative because we do get positive curl in different spots, okay? All right, so that's my demonstration on curl, so you can get a visual of what is going on. Now remember that the determinant, when you're calculating the determinant, you kind of have this right-hand rule thing. You know, if you calculate a cross product, you have a right-hand rule thing. So if you have A cross B, you use your fingers and your thumb is pointing in the direction of the curl. So for us on a 2D vector field, the curl points out of the plane, straight out. Okay, so very important fact, just in case you didn't hear me say it already, the curl of a gradient vector is 0. This means that if a vector field is conservative, its curl will be 0, okay? And vice versa. If the curl is 0, then we know the vector field is conservative. So what this means now is that we have a way to determine if a 3-dimensional vector field is a conservative vector field. We did not have that ability in the last couple of classes because we didn't know what the criteria was. We were just told to determine if a vector field is conservative, show that del Q del X is equal to del P del Y. But that didn't say anything about any derivatives with respect to Z. Now we have it. Okay, so let's calculate some curls. Do this one more here. We've got f of x, y, z. The components are 0, x cubed, yz squared, and y to the 4th z cubed. So I'm going to set up my curl. Curl of f is that upside down triangle vector crossed with f. Set this up in a determinant. We have I hat, j hat, and k hat across the first row. We have del del x, del del y, and del del z across the second row. We have 0, x cubed, y, z squared, and then y to the 4th z cubed in the third row. Okay, once again, I'm going to highlight where I start and cross out that row and column. So I start off with this is equal to I hat times, and then I've got to get my 2 by 2 determinant, del del y of y to the 4th z cubed minus del del z of x cubed y z squared. Okay, and then we can go ahead and erase those highlights, erase those arrows, and now we'll focus on j. Remember, we have a minus sign with j, so minus j hat, and then our 2 by 2 determinant is del del x of y to the 4th z cubed minus del del z of 0. I need to move this a little bit. Okay, and then finally we have, let's get rid of those highlights. We have our last component k. Cross out the row and column, and we can focus on our 2 by 2 determinant that we need to calculate. So we get plus k hat and then del del x of x cubed yz squared minus del del y of 0. Okay, again, I didn't calculate any of my derivatives. I'm going to do that now. So for the I hat, I have del del y of y to the 4th z cubed. That'll be 4y cubed z cubed minus del del z of x cubed yz squared will be 2x cubed yz I hat, and then minus del del x of y to the 4th z cubed is 0, minus del del z of 0 is also 0, so my j component will be 0, plus del del x of x cubed yz squared is 3x squared yz squared. Oops, don't close that yet. Minus del del y of 0 is 0, and then I have my k hat. Okay, again, I'm going to rewrite this in angle bracket notation. I prefer it just because it also highlights any of my components that are 0. In my first component, I have 4y cubed z cubed minus 2x cubed yz. Second component is 0. Third component is 3x squared yz squared. And that's my curl. That's it. All right, next. Let's see what we've got. We're asked to determine whether the vector field is conservative. So now we have our tool. And if it is, we're going to find a function little f, the potential function, such that this vector field is the gradient of little f. So this is not new. We did this in the last section, okay? Or in fundamental theorem of line integrals. We were determining scalar potential functions for our vector fields. The only part that's new is being able to show that a three-dimensional vector field is conservative. Before we had to assume it. All right, so we're going to determine whether this is conservative. So we'll know that f is conservative if curl of f gives back the 0 vector. So let's figure that out. Curl of f is equal to that upside down triangle crossed with f, which is going to be our 3 by 3 determinant, I, j, and k, del del x, del del y, del del z, and then my components are ln of y, x over y plus ln of z, and then y over z. Okay, so the hope is that we get back 0, 0, 0. Okay? All right, so I'm going to go ahead and give myself more space. We have our I component, and we're looking at del y of y over z minus del z of x over y plus ln of z. And close that. Minus j hat. And then we'll look at del x of y over z minus del z of ln of y. And then plus k hat. I don't know why I wrote a comma. Get rid of it. Okay, plus k hat, and then there we'll have del x of x over y plus ln of z minus del y. I'm running out of room. Of ln of y, close all those parentheses. Okay, let's go ahead and take derivatives. In the I hat component, del y of y over z is 1 over z, minus del z of x over y is 0, del z of ln of z is 1 over z. So that's my I hat component. This is so far so good. I'm going to get 0 in the first component. Minus, in the j component, del x of y over z is 0. Del z of ln of y is 0. So I'm pretty happy in my j component. Plus, for k, I have del x of x over y is 1 over y, and del x of ln of z is 0, minus del y of ln of y is 1 over y, and that completes my k component. It looks like we got back a vector with components that are all zeros, which we can write as 0 with a hat sitting on top of it. Okay, curl of f is 0. Yay, f is conservative. So what we have to remember is that now that we know f is conservative, we can say that f has components that are first partial derivatives of our potential function that we're going to try to find right now. Okay, so that tells me that ln of y is f sub x. X over y plus ln of z is f sub y. Y over z is f sub z. So I'm going to do partial integration to work backwards and find my f of x, y, z. So let's start with f of x, y, z, in theory, should be the integral of f sub x dx. Okay, so I go and I pull up my f sub x. We're told it's ln of y. We're going to integrate that with respect to x, and we'll just get back x ln of y. Plus, our constant of integration, we'll call it h of yz, since y and z would all be treated like constants in an integral with respect to x. The next one, x over y plus ln of z, we take f of x, y, z, and we integrate f sub y dy. That means we're integrating x over y plus ln of z dy. Okay, now I'm seeing that first component, first term is x over y, and x is just a constant, so I'm really integrating 1 over y, which is ln of the absolute value of y. So we get x ln of the absolute value of y, plus the antiderivative of ln of z is going to be y ln of z, plus some constant of integration. We'll call it g of xz. Okay, last but not least, f of x, y, z could be that we're going to integrate f sub z dz. And maybe we'll get more parts, maybe we'll just get some repeats. So f sub z was just y over z, so we're integrating y over z dz. Remember that y is just a constant, so we're really integrating 1 over z, which is ln of the absolute value of z, plus q of xy, the constant of integration. All right, so we have 3 representations of f of x, y, z. One of them is x plus ln of y. The other one is x ln of y plus y ln of z. The third one is y ln of z plus q of xy. Okay, so it looks like if we put that all together, we are going to have our true f of x, y, z. So from the first f of x, y, z that I have there, I'm going to get the x ln of y. Okay, in the second one in orange, I have f of x, y, z is x ln of y, so that confirms, yes, we don't write it again, we already wrote it. But the second term, y ln of z, was new, so I'll put that in. Then we go to the third representation, and it's y ln of z. I already wrote it, not going to write it again, so that's it. All right, those are my functional parts of f of x, y, z. Of course, then we have a plus c. Okay, so that's it. The only new step here was showing that we actually had a 3-dimensional conservative vector field. And then from there, we're kind of doing a repeat of what we did in 16.3. Okay. Next topic is divergence. Okay. So the divergence is again going to be us operating with the del operator. Remember, the del operator is the vector with the operators of del x, del y, and del z. But we're going to look at what happens when you dot product that with a vector field. So we're going to dot it with a vector field that has p, q, and r. Here's our notation though. Div of f is how we write divergence of f. What we're doing is the del operator dotted with f, and then here it is written out. Remember, with a dot product, you multiply like components and then you add everything together. So when we multiply like components, we get del x of p, which we can just write del p del x, plus del y of q, which we write as del q del y, plus del z of r, which we write as del r del z. Okay, you don't have to memorize that. You can just simply write out these vectors and then compute the dot product. The divergence is a scalar function. So anytime we've calculated a dot product, the result was a scalar. It's like a number, or in our case, it'll end up being a function, but it won't be a vector. Okay, so a scalar function is considered to be non-vector. Now, if our vector field is the velocity of fluid, so I'm going to go back to the fluid example, then the divergence just represents the net rate of change of the mass of fluid flowing from a point per some unit volume. In other words, what we're looking at is the tendency of the fluid to diverge from a point. And physically, what that means is that the divergence is telling us the extent to which each point in space is a source of fluid, that would be positive divergence, or a sink of fluid, and that would be negative divergence. And when the divergence is zero, we say that the fluid is incompressible. Now, to me, none of that really makes a whole lot of sense, especially if this is the first time I'm reading about this. And so I have another example, and I'm just going to read it to you because it's really, I don't know, I found it very enlightening. Another way to think of this is to consider the case of water flowing through a large pipe. And there are smaller pipes joined to the large pipe. As the water flows, more water is added along the way by the smaller pipes. Therefore, the mass flow rate increases as the water flows past those points of entrance from the smaller pipes. If, however, there's a leak in the main pipe, then the mass flow rate will decrease as it flows past that leaky point. The change in the flow rate, whether it's increasing or decreasing, is called a divergence. If the initial flow rate is less than the final flow rate, right? So in the beginning, your flow rate is low, and then at the end, you have much higher flow, then the divergence is positive. That means there was a source of fluid, okay? If the two quantities are the same, in other words, right before the point and right after the point, there was no change whatsoever, that means there was no source, there was no sink, we didn't lose any fluid, we didn't gain any fluid, the divergence is zero. If the initial flow rate is greater in the beginning and then it goes through a point and now the flow rate is less, that means that we lost some fluid, there was a sink of fluid, and so then the divergence is negative. So my hope is that, when you're calculating divergence, maybe you'll picture these water pipes and what's happening and what these numbers actually mean, okay? Now, there are other examples of divergence other than water pipes, okay? But it's one example, and it's the one that makes sense for me. Maybe for you, you come up with a different example of flow and how you could have sources or sinks in that flow of whatever it is you're thinking of, okay? Now, the actual calculation is very simple and straightforward. In this first example, we are asked to find the divergence of big F of x, y, z. The components are x squared plus y squared plus z, and x, y, z. So to find this divergence, we're gonna write out what it is we have to calculate. We have div of f, and that just means we're gonna take the del operator and dot it with f, which means that we have del x, del y, del z for the del operator, dotted with f that has x squared plus y squared plus z, and x, y, z in its components. Now we compute the dot product. So we take del x of the first component, x squared plus y, plus del y of y squared plus z, plus del z of x, y, z. And then we go ahead and take those derivatives. We end up with 2x in the first one, plus del y of y squared plus z is 2y, plus del z of x, y, z is xy. And this is the function that we get, the scalar function that we get when we calculate the divergence of whatever this vector field is. Now, if we knew a particular x and y value, then we could calculate a numerical value for the divergence. If x and y are equal to 0, it looks like we would get that the divergence is 0. And so that would mean, remember, that there's no change in the flow rate, in the amount of the flow rate. And so that would mean that the flow rate just goes right past the fluid just goes right past the point, no changes, there are no sources, no sinks whatsoever. If x and y were negative, of course, this would be a negative divergence, which means there was a sink. We lost some fluid. And if x and y are positive for this particular one, it looks like we'd have positive divergence, which means there's a source. Okay? All right, so we're told that if F is a vector field in the three-dimensional reals, so R3, then the curl of F is a vector field on R3. And so we should be able to compute its divergence, right? We can calculate the divergence of any field, any vector field. And then we are also told that this result will be, well, they tell us the divergence of a curl vector is always going to be 0. And then the flip side of this is that if the divergence of a vector is 0, then that vector was a curl vector. And we're asked to prove this. It's a little painful. So oftentimes in proofs, the issue is that it's hard to know, well, what do I use as an example? And the problem is you don't use a specific example. You have to use a general example. And so by general, what I mean is we are going to, well, I'll show you. We're going to calculate the div of a curl vector. What is a curl vector? We just write that generic form where the derivatives show in terms of p, q, and r. So the div will be the vector with operators del del x, del del y, and del del z, dotted with the vector that's the curl vector, which I have it written down in front of me, so I'll write it out. Del r del y minus del q del z. Then we have del p del z minus del r del x. And finally we have del q del x minus del p del y. So now I need to do the dot product. And that means I take like components and I multiply them. So I'm going to be taking del del x of del r del y minus del q del z plus del del y of del p del z minus del r del x plus del del z of del q del x minus del p del y. Okay, I have to go ahead and send everything through. If I take del del x of everything inside here, I get del squared r del x del y minus del squared q del x del z plus del squared p del y del z minus del squared r del y del x plus del squared q del z del x minus del squared p del z del y. Okay, I am going to gather some like terms. I'm going to put the del squared r's together, the del squared p's together, and the del squared q's together and see what I observe. So just reorganizing now. Del squared r del x del y minus del squared r del y del x plus del squared q del z del x minus del squared q del x del z plus del squared p del y del z minus del squared p del z del y. Okay, now this is going to be pulling something from 2 chapters ago, from chapter 14. What we learned in chapter 14 about mixed partials. If we are dealing with continuous functions, p, q, and r, and they have continuous first derivatives and second derivatives, then the mixed partials are equal. Okay, what that means is that del squared r del x del y is equal to del squared r del y del x. The same is true with Q. We're just looking at different orders. With respect to del Z, del X is equal to with respect to del X, del Z. And similarly for the last one. This is all by Clairaut's theorem. Clairaut comes up quite a bit in mathematics. So then we put that all together and we get that it's equal to 0. All right. So the point of that wasn't so that you can go through the pain of proving something, but it's more so you understand why when we take the divergence of a vector field that is a curl, we will get back 0. And then, of course, the other implication that if we end up with a divergence that is 0, then we know that that vector was a curl vector. Okay. Now, true or false, and why, would the curl of a divergence be 0? Let's check this out. Curl of the divergence of f. Well, what is the divergence of f? Is it a vector or is it a scalar? Well, divergence is a dot product, and so a dot product gives us a scalar function. That means we're trying to calculate the curl of a scalar function. But a curl requires a cross product, and a cross product requires two vectors. So this is not possible. You cannot take the curl or a cross product when one of the vectors is just a scalar function. You need two vectors. So then number 4, for a fluid with velocity, big F equals the vector with components 2y squared and x plus z, is the fluid diverging at the point 1, 2, 1? Well, in order to answer that, we have to know what the divergence function is. Okay, so first, we're going to find the divergence function for big F. Okay, so that means we need to calculate divergence of F, which means we're looking at del x of the first component, which is 2, plus del y of the second component, which is y squared, plus del z of x plus z, the third component. Calculating those derivatives, I get 0 plus 2y plus 1. Or in other words, it's just 2y plus 1. Okay, so the divergence function of f is 2y plus 1. We want to know, is the fluid diverging at the point 1, 2, 1? Well, let's look at that. The divergence of f of 1, 2, 1 is equal to 2 times the y value, which is 2, plus 1, which is going to be 5. And that does not equal 0, which means there is divergence. And also, because the divergence of f of 1, 2, 1 is positive, we know there is a source. If we had gotten a negative value, we would know that there was a sink. So that's just one example of where we can use that. Now for the following vector field, we're going to examine several places on the graph and see where we think the curl might be positive or negative or 0. And the function that's here is big F is equal to sine of y cosine of x and 0 for components. Now, what we're going to do is kind of move from left to right and look at the direction of the rotation that's happening at a particular point, okay? So there are some regions I can look at in particular. I can look at a region right here, and the direction that the vectors are turning in is clockwise. And if you recall from what we learned in 16.4 about orientation of a curve. It's very similar for the orientation of a vector field. If we have clockwise rotation, that is negative. Okay, so the curl is going to be negative right here. Maybe I should just write negative. On the flip side, over here, just slightly up and to the right, I see that the rotation is counterclockwise, which would mean that we have positive curl. So I'm going to look for negative rotation and positive rotation and put circles in those spots and see what's going on. So let's find some more positive rotation. Looks like right here we have counterclockwise, so that's positive. Down here we have counterclockwise, so that's positive. Down here we have counterclockwise, so that's positive. And then right here, whoops, I meant to use purple. Right here we have clockwise rotation, so that's negative. All right, but we were asked about where it might be zero as well. So notice in between the negative and the positive, there are some vectors that are just very nicely flowing straight through. You can see a nice long region of those right here. Okay, so those are all zero. Zero curl there and there. Zero curl there and there. That's all I was looking at. Don't have to calculate anything. I mean, I could calculate the curl and then I could plug in points and I could determine, but this was a little easier. So we need to be able to do the algebraic method of calculating curl, but it's also good to be able to look at a vector field and decide whether you see rotation or not, and whether that rotation is positive, negative, or none at all. All right, next one. For the following vector field, we are going to be looking at the divergence and where we think that the divergence might be positive, negative, or zero. And we've got our vector field here. And so I want to write out a few bits here for us to be able to follow. So bigger, and by bigger, I'm talking about the bigger vectors. When they go from bigger to smaller, that means that there is decreased flow rate, and so that implies a negative divergence. If there is no change in length, that implies approximately, and I don't want to say equal, but it's approximately zero divergence. And then if we're going from smaller vectors to bigger vectors, then that means we've got a source, and so that's going to be positive divergence. Okay? So we're going to find all the positive and all the negative. So on the far left, I'm noticing really long vectors that I'm looking vertically up and down right here. See the vectors, the lengths are getting shorter and shorter, so we're going from bigger to smaller, and quite fast. I would say that this is a large negative. Then there's, let's see, are there any others? No, we're good from there. Another region right here, just to the left of the y-axis, they're still negative, but I would say it's a small negative because the change in the length of the vectors is less drastic. Right in the middle, and I may have kind of hurt my, let me fix my these a little bit. So I've got my large negative right in here, got my small negative right in here, and then right in the middle, right around the y-axis, and you'll see now why I had to change things. look at the vectors that are directly to the left of the y-axis, and then look directly to the right. Notice they are the same length and size, or approximately the same length and size. There's almost no change. So we could say that's approximately 0 for the divergence. And then we can look just a little bit to the right of that, and we can see a small positive change. And we can look to the right of that and see how the vectors are growing much faster, much bigger, and that's a large positive change, okay? Or in other words, a large positive divergence. So that's all we have to do. We're not going to calculate the actual divergence. We can just look at a graph and kind of make some assumptions based on the lengths of the vectors. That's it. All right. So this next one, we are asked to show that the vector field, big F, is equal to the vector with components xz, xyz, and minus y squared. We want to show that it cannot be written as a curl of another vector. So that seems like such a weird question, like a weird thing to try to do. We want to show that that it's not a curl. That's what we're trying to show. So what we have to recall is, if the divergence of the curl of F is equal to 0, then, well, let's say this. I don't want to have that. Let's call it G, okay? If the divergence of G is equal to 0, then G must be the curl of some other vector F. That's how I want to write it, okay? We found that the divergence of a curl vector is 0, and then there was a statement right after that that said on the flip side, if the divergence is 0, then you were working with a curl vector, okay? So what we're going to do is say, all right, well, let's calculate the divergence of it. If we get 0, then we know our vector was a curl. All right, so let's calculate the divergence of F if the divergence of F equals 0, then F is equal to a curl vector. That's all we have to do. All right, so let's calculate div of F. Div of F, we're going to be looking at del x of the first component, which is xz, plus del y of the second component, which is xyz, plus del z of the third component, which is minus y squared. And what we get, del x of xz is z, plus del y of xyz is xz, del z of minus y squared is 0. So we didn't get 0. Therefore, F is not a curl vector for any other vector field. Okay, so we had a lot of, just calculation-based problems in this section, but we also had, kind of a little bit of introduction to proof. In, now that we know stuff, can we use that stuff to prove something? That was kind of the point of it. All right, so that is a conclusion to the curl and divergence section. When we meet next again, we're going to be working on surface areas, and so it'll feel like another drastic change in what we're doing. But today was really just about learning a couple of tools that we're going to need to calculate some future integrals. So if you have any questions while you're doing your homework, please reach out.